thank you very much and welcome. My name is Yuval Boger. I'm Chief Marketing Officer of Classiq. And today we've got a really fun and exciting webinar with a gazillion different presenters from all over the world. So let's jump right in and let me explain what our agenda, what we're going to try to do today. I'll spend a minute or two just talking about Classiq and the Classiq Platform. And then after that, we'll do 4 segments that have to do with 4 of the 4 competition problems. We had the Classiq Coding Competition a couple of weeks ago, and we're going to go one by one, talk about the constraint satisfaction problem, the Hamiltonian exponentiation problem, the log normal state preparation, and then the MCX problem. Then we'll have a segment with Dr. Yehuda Naveh, our co-founder and CTO, and hopefully we'll have a little bit of time for Q&A. We've got speakers really coming from many corners of the world today. So first, 3 of our competition winners. Ozlam, I believe you're coming to us from Poland, is that correct?
I am located in Turkey, but I'm working in Poland.
Excellent. And then we've got Diogo, that I think you're from Portugal, and Soshun, you're in Japan. Is that correct?
Yes.
Yes, that's correct.
Excellent. I have 2 of my marketing colleagues here, Eric and Hannah, that are located on the East Coast of the United States. I'm usually in the US. Today, I happen to be in the company headquarters in Israel, and our co-founder, Dr. Yehuda Naveh, is also in Israel. So just a few words about Classiq. We believe we are the leading quantum software company in the world, taking quantum software to a higher level. Fairly young company, started in 2020. By now, we've raised about $63 million of capital, so we're very well funded to have one of the best engineering teams in the world. We have over 40 quantum engineers, software engineers, computer scientists, quantum information scientists that are all working on creating a platform to make it easier, faster, better to create sophisticated quantum circuits. Some of this work ends up manifesting itself in patents that we file. And by now we have customers in various industries, various parts of the world. The problem in quantum, and as Yehuda told me the other day, is that quantum software is easy to define, but is hard to implement. It's very easy to say, oh, I want an oracle that does XYZ, but taking that statement and converting it into a quantum circuit that works, that's efficient, that I didn't forget to uncompute anything, is difficult. And that's, of course, just a simple example of growth, but it gets harder and harder. It also gets harder as you want to run this efficiently on various types of quantum computers that may have different native gates, different number of qubits, different set of capabilities. How do you take the circuit from one and do it on the other? And the other thing, which was sort of a focus of the quantum coding competition, was creating efficient circuits. Efficient circuits, meaning circuits that use fewer resources, fewer 2-qubit gates, or shorter depth, and so on, are important because for 2 main reasons. One, as we live in the NISQ era, then having more compact circuits usually allows you to get more accurate results. And 2, because most of the quantum computers have very limited resources. If you can make circuits that are more compact, then you could potentially fit larger problems into a given computer. We try to solve that without forcing the user to understand or to dig into the individual gate level. Basically, we've built a platform, the Classiq Platform, that takes 2 types of inputs. The first is a high-level functional model. What is it that you're trying to do? This could be a finance model, this could be a optimization problem, and try to express it in a high-level language. Then we take a list of constraints. These constraints could be, I have only 20 qubits that I can run on, or I want to use this set of native gates, or I want to do something else. And then our platform explores a huge design space, looks at millions and millions of different options, different implementations, to try to find an implementation that delivers the functionality while meeting the constraints. And it's interesting because you could change the constraints because you may want to move from one computer to the other, or you now have access to a larger computer, and you'd get a completely different circuit, which would still meet the functionality and meet the constraints. We allow the designer to focus on what is it that you want to do, and our platform takes care of the rest. Here is a very, very simple example. This is a Grover search. And so you can see a functional model that defines the oracle in symbolic way, and then a list of constraints, the number of qubits, for instance. And then with a click of a button, this gets analyzed and transformed into a working circuit that you could execute, you could debug, you could investigate, and so on and so on. And one of the things we're going to do in the next 4 segments as we go into the competition, we're going to present the problem for each of these challenges. We're going to talk about the winner, show how the winning solution was, and then we'll show how you can solve the same problem using the Classiq platform. And we can compare the results a little bit. And I think you'll see in general that the gold winners did fantastic work in optimizing the circuits, and they got circuits that are a little bit better than the automatic solution, but the automatic solution is automatic. It works within a couple of minutes. So if you have 1 to 3 weeks to hand optimize the circuit, you might be able to do a better job than the automatic solution. But if you just want to go, and want a solution that works and is compact and efficient, then using Classiq may be a good way to start. So let's jump right into it and talk about the first problem, the constraint satisfaction problem. And I think, Hannah, this is something that you're presenting. So
Correct.
Please explain the problem, and then we'll go to Özlem to explain her solution.
Perfect. Thank you, Yuval. So constraint satisfaction problems are everywhere. We live in a constrained world, and these types of problems are one of the most promising types of problems solved by quantum computing. So for this challenge, we gave the competitors a cockroach logic puzzle, which is an example of a SAT problem, with the goal of filling in the puzzle following a set of constraints or rules. This cockroach puzzle must be solved with the given constraints using Grover's search algorithm, and it must be decomposed into single qubit and C0 gates. Another condition is the constraints cannot be hard-coded. Each cell within the puzzle must be associated with a quantum register, so the quantum code actually goes through with solving the problem. And then the winner was the circuit that is valid with the fewest C0 gates in the oracle. Now, this is the grid, the cell of the cockroach puzzle, as well as the listed constraints. And this problem was a challenge in constraint implementation. So the rules of cockroach was filling in the cells such that each cell in the row and column is unique. So we have inequality and equality checking constraints, as well as each cell in the row and column adding up to the given number. So a arithmetic constraint.
Excellent. Thank you very much. And Özlem, I'll stop sharing. And if you're able to, please share your screen. And we'd love to hear how you were able to solve the puzzle.
Thank you. So let me first present myself. So this is Özlem, and we joined this challenge together with my colleague Adam Gloss. We are working both in Institute of Theoretical and Applied Informatics in Polish Academy of Sciences. Adam is also working in the company Algorithmic. And we are also both affiliated to QWorld, which is a non-profit organization for promoting quantum technologies through educational activities. Let me move on to our solution. So first, let's check the general solution. The idea is to use Grover's search to solve this problem. Here, you've seen that there were some variables, and if those variables are binary, you can represent each one of them using a qubit. So that if it's 0, it's 0, and if it's 1, it's 1. And if it's not binary, then you can use more than one qubit to encode the variable. And then the idea is using an oracle so that we can mark states that correspond to correct assignments for those variables. And then using Grover's search, we can find out the correct assignment. So this is the general idea. In Grover's search, we start an equal superposition of all possible states. You can see here in the initialization stage, we have Adamar gates, which creates an equal superposition of all possible assignments to the binary variables. And here you also see the diffusion operator, and this diffusion operator in Grover's search also uses this initialization step within the diffusion operator. And those two, oracle and diffusion, are repeated. Now, in our solution, actually, our solution depends on this generalization of Grover's search, which is known as amplitude amplification, where you don't need to start in equal superposition state, but you can start in an arbitrary customized initial state. But actually, what inspired us was this Grover mixer QAOA, because this was something we were working on. And in this Grover mixer QAOA, for those who know QAOA, instead of starting in equal superposition, as in this generalized Grover search, you start in some special initial state, which you create through a unitary matrix, through a unitary operator. And you also use this within your diffusion operator. And we even, and we even use this in new method we have for implementing QAOA in an efficient way, which we call fun QAOA. So this was mainly our inspiration in solving this problem. And if we now check our solution, here we replace this initialization step. Instead of Adamar, we use some special unitary, and accordingly, the diffusion operator is updated. And the idea here is that to encode some of the constraints within the initialization step, so that when forming the oracle, we don't need to check all of the constraints, but some constraints are already handled by the initial state preparation. This will be clear in the next slide. So we divided the constraints into two, and some of the constraints, for instance, this one is saying that x0 is not equal to x2 and x0 is not equal to x1. So this means we cannot have a state like 1, 1, 1, where x0 is equal to x1 and x1 is equal to x2. And so based on this, instead of starting in equal superposition of all states, we started in this specific state. And to do this, we used some CNOTs and Adamars to prepare this initial state. And since we handled those constraints with initial state preparation, then only those remaining constraints were left. And we implemented those only within the oracle. And in this case, the idea was to store the information about the satisfaction of each constraint in some qubits, so that if it is 1, then this means constraint is satisfied, and if it is 0, it is not satisfied. And those inequality checks, they were done through XORing. So this was the main idea, to remove some of the constraints from the oracle part of the initial state preparation. And what is the advantage of this? So first of all, you need smaller number of Grover iterations because we are working with a smaller subspace. And we had a simpler oracle because we did not check all of the constraints within the oracle. This resulted in a reduced CNOT count. We further optimized our circuit by, for instance, implementing the multi-control Z gate, which is needed for marking the correct states. We implemented this through relative phase Toffoli gates, which are less costly than the ordinary Toffoli gates. And some constraints were implemented in place. This means we didn't use additional qubits for checking some of the constraints, and this also helped reducing CNOT count. And what can be the disadvantage? In our case, we have a more costly initial state preparation, and also more complicated and costly diffusion operator. But in the end, we were able to reduce the C0 gate count 86 in our solution. And this is just a picture of how our oracle looks like. You see that there is computation and uncomputation at the end for checking the satisfaction of the constraints. And in general, this is our solution. Thank you for listening, and I will be happy to answer any questions.
Thank you very much, Özlem. Let me take the presentation back just for a second. So indeed, thank you very much for this. Özlem and Adam won the gold medal in this competition. We received a good number of submissions. You can see here the graphs in the showing on the y-axis the number of C0 gates, anything from the winning solution all the way to solutions that had 1,000 C0 gates and many in between. And Hannah, if you could please demonstrate the Classiq solution, how it works, and what we were able to achieve there.
Sure thing. All right. So here we have a Jupyter notebook with our Cockroach solution. So we just have some simple import statements and then defining of our arithmetic expression. So each of our constraints, and then we plug this expression into our arithmetic function, defining each of our variables as a quantum register with size 1, except x3, which is known to have 2 qubits. And then we specify our basis gates of C0s and unitaries and optimize for our C0 gate count in our constraints. Then we simply synthesize, and I'll do that now. And we're also displaying an interactive circuit that'll come up in a second. So right now, our model has the functionality of the circuit, the arithmetic expression with the certain variables, as well as the hardware constraints, meaning the C0s being optimized and the basis gates. So this model is getting sent to the cloud, and Classiq has our synthesis engine performing robust calculations on all of the, or a large majority of the circuits that have this functionality that meet these constraints. And using those calculations, we eliminate many of the possible circuits and return the best circuit in this case. So in a few seconds, we should have a window pop up with our interactive circuit. I have a already expanded version here, if you're curious while we wait. So we can see this display lets us see each of our constraints as the gate view or the functional block view. I believe it might take a little longer because my Zoom is running. But as you can see here, we have our logical AND being implemented by 9-control MCX. So similar to the MCX problem, we have some optimizations going on in here, except this one is optimizing for C0 count.
Excellent. And I've got 2 quick questions. Maybe Özlem, you could answer them, or Hannah, if you want. One was, how did you pick the conditions that needed to be implemented within the oracle and the ones that were implemented in the initial state? Is there any way of efficiently picking them automatically? I think that's a question for you, Özlem.
Actually, so for instance, there was a constraint saying that x3 is equal to 2, but it was forbidden to encode it through the circuit. So it will be like hacking because it's 2. So for instance, we did not encode this as the initial state. We left it to constraints. And this is also related to the other question about the order of the initial state. Yes, there is a reason why we had this order, because using this order, it was more efficient to create this special initial state through the usage of Adamars and C0. So this is how we created the specific initial state. And those constraints like x1 is not equal to x2, x2 is not equal to x3. Actually, those were the ones we used for initialization. And those were really suitable for creating the initial state.
Excellent. Thank you very much for that. And I think that's also related to another question that we had is there a reason to put the order of the initial like x2, x1, x0 instead of the normal order x1, x0, x1, x2?
There were some constraints like x2 is not equal to x0, x0 is not equal to x1, x1 is not equal to x6, and so on. We had the specific order to optimize the number of C nodes, because then we were able to create some superposition and then use C node to generate the specific constraints.
Excellent.
So it was on purpose.
Excellent. So let's move on and let's talk about the Hamiltonian simulation. And Eric, would you like to jump in and describe the problem, please?
Absolutely. So Hamiltonian exponentiation, right, otherwise known as quantum simulation, is one of the most important applications for quantum computers and one of the reasons behind its development. One of my favorite quotes in quantum computing is from Richard Feynman, who said that famously, nature isn't classical, so if you want to make a simulation of nature, you better make it quantum mechanical. Right, classical computers just simply cannot calculate efficiently quantum simulations, right? So the best system for a quantum simulation is, to no one's surprise, a quantum computer. So the problem that we devised for this was to generate a circuit that approximates the Hamiltonian exponentiation of lithium hydride. We provided the polystring for the contestants. The conditions for the problem were the circuit had to have no more than 10 qubits, use only single qubit gates and C0 gates, and the unitary operator error had to be less than 0.1, and the circuit with the shortest depth wins. Perfect. So this problem was largely a challenge in gate cancellation. The most common algorithm that we're using for this is the trotterization method. We have the Suzuki trotter formula up here. And this formula is really useful in the context of quantum simulations, since generally these Hamiltonians are given by a sum of polyterms, and polyterms can be easily exponentiated as shown. So we're showing an example of what contestants had to do in this problem. We're showing here two circuits in that next line, showing a Hamiltonian exponentiation, which is ZZZ plus ZZ, and it can be expressed in one of two fashions. If you express it in the left, that's as short as it can get, but if you express it in the method on the right, you can do C0 gate cancellations and have a shorter gate depth. So it's about how do you implement this circuit and how do you cancel out these gates intelligently?
So let's see how it's done. The winner here was Diogo Cruz. And Diogo, would you mind talking a little bit about how you solved this problem?
Yeah. Okay. So as you've all just said, I'm Diogo Cruz. I'm the winner of the Hamiltonian Simulation Challenge. I'm a PhD physics student at the Instituto Superior Técnico in Lisbon. And usually I mostly work on quantum algorithms, not so much in Hamiltonian simulation. So for this challenge, we wanted to simulate this particular Hamiltonian for a time t equals 1. And at this scale, we can actually start by discarding some of the more negligible terms. If we do so, we reduce the number of terms that were initially 276 to 204. This adds a bit of truncation error, but that's below the threshold that we're trying to avoid. Now, on top of this, we're also going to use a trotterization formula, in this case, just a simple Lie trotter formula with one time step. And we want to minimize the error that this trotterization is going to add to our implementation. We can use some of the techniques from this paper here on the right, where they show that by solving a minimum click cover problem, you can order the polyterms in your Hamiltonian in such a way that within each group, all of the polyterms mutually commute with one another. And that then gives you a lot of freedom to play around with your particular implementation. If you do this for this truncated Hamiltonian, you end up with about 14 groups in my submission. This paper is actually focused on reducing the C0 gate count, not the depth count, and it uses ancilla qubits, which we don't have here. So we need to use some new approaches to optimize our circuit. So after we have those 14 groups, within each group, we start by trying to parallelize as much as possible the different polyterms. We can do this, find the optimal way to do this, by solving another minimum click cover problem. So this gives us an implementation that is highly parallelized. Once we do this, we know that if we order these terms in such a way that the most similar terms are next to each other, then it's more likely that this will result in more gate cancellations. So we want to try to minimize the difference between neighboring terms. We can do this by solving a traveling salesman problem, as you see here on the right. And so now we have not only the terms highly parallelized, but also a good ordering that should lead to a high number of gate cancellations. Now we actually need to convert these polyterm evolutions into actual gates. There's a lot of freedom in how to do this. And one thing we can control is the particular qubit in which we're going to implement the Z rotation that encodes the time evolution in our simulation. We want to, similarly to what we were doing before, we want to try to keep this qubit the same for neighboring polyterms, because if we keep it the same, it's more likely that gates will cancel out, especially C0 gates. You can see in this simple example on the right that it's better for us to implement this rotation in the middle qubit for these three terms, because a bunch of C0 gates cancel out, than the suboptimal choice of using the first qubit for the first terms and the last qubit for the last polyterm. So finding this optimal qubit for every term can be done by solving a minimum set cover problem. Once we've done all of this, we actually have a circuit with a bunch of C0 gates and single qubit gates, but we can go one step further and apply the optimization techniques of the packages PyZX and Qiskit to end up with a final depth of 671. So on top of the 0.06 error that we got from the initial truncation, we now have an extra totalization error for a total error that's slightly below the 0.1 error that we were trying to avoid.
Excellent. Thank you so much for that with all the different optimization algorithms. This is the graph showing the circuit depth versus the number of submissions. And Eric, if you wouldn't mind, let's talk a little bit about how Classiq solves this problem and how Classiq can tackle even more sophisticated problems.
So the first thing we do is to load in the monster polystring that we provided to all the contestants. We just label that LIH. I'm going to import Classiq. I'm already authenticated in the system. And performing the Suzuki trotter is quite simple with the Classiq platform. I'm calling out Suzuki trotter function. I'm saying that I want to load in the poly list that I just labeled as LIH before. My evolution coefficient is 1. My order is 1, and my repetition is 1 for the Suzuki parameters. Now, most contestants found out quite easily and quickly that you only need 1 repetition to stay within the error we provided. After you define that, you call our model designer. You say, Classiq, please design this circuit. We're designing a Suzuki trotter with these parameters, and synthesize it for us. Once that's all done and said, we can go ahead and show an interactive circuit to show our, I believe it's about 1,057 is our circuit depth compared to Diego's 671. But we had answers ranging from 671 to, I believe, 16,000. And out of the over 20 or so submissions we had for this problem, about 12 of them actually met the constraints of the problem, showing that it's not only difficult to make optimized circuits, it's difficult to make quantum circuits that meet the parameters and specifications that you're trying to implement. Again, showing that it's easy to describe what you want, but it's hard to implement at the end of the day.
And Eric, what you're showing on the screen right now, is it a circuit that was just generated this minute?
Yep.
By running the Jupyter Notebook?
Yep, I ran the Jupyter Notebook live and it just generated. So we have our full Suzuki trotter of about 1,057 gate depth generated in about 30 seconds or so.
And if you wanted something more sophisticated, I don't know, H2O, would that be possible as well?
Absolutely. All you would need to do is go ahead and load in a different polystring. Now, Classiq Platform can also generate polystrings for you. You just have to define what that molecule is.
Excellent.
Mm-hmm.
So let's move on to the next problem, which I think is the log normal one. And here we don't have we certainly had winners, but we don't have the winner presenting the solution. So let's try to do it just a tad more quickly to leave enough time for questions and all the other segments that we want in this presentation. So go ahead, Eric.
Absolutely. So we're going to go into our log normal state preparation. Let's see. All right, perfect. So state preparations are an important part of almost every single quantum circuit. You need to initialize your circuit to be able to perform calculations after the fact. Whether you're loading in your assets for a financial portfolio optimization calculation or the vectors for machine learning, most every quantum circuit needs some kind of initiation to perform their calculations. So this problem was to develop a circuit that initiates a log normal distribution. The conditions were similar to the last one: no more than 10 qubits, must be made of only C0 and single qubit gates. You must provide the discretization method used, which was a little hint to our contestants, and the distribution area must be less than 0.01. And again, the circuit with the shortest depth wins. So there were actually two ways to think about this problem. This was a challenge in creativity, where the last one was a challenge in gate cancellation. Here we wanted to show that it takes more than just technical knowledge to develop efficient quantum circuits. It also takes outside of the box thinking. So there were two ways to solve this. You have the straightforward way, where you load in a probability mass function into your qubits that approximates the desired probability distribution that you're going after. And the out-of-the-box method is to manipulate the discretization method so that you're able to load in the same probabilities for all of your qubits, yielding essentially the probability distribution of your choice and a very short circuit. So here's a little bit of the math, just going through, why this is possible in the first place, right? So, why can we manipulate this discretization? So we see this error calculation. To minimize it, we go ahead and look at that last term. We expand it out. It's a polynomial term, and we can minimize that, showing that essentially it makes intuitive sense. The error is minimum when a given loaded probability matches the probability distribution for a given discretization bin. What that means is that mathematically customizing the discretization spacing yields the same exact results as customizing the loaded probabilities. So setting our measurements in the, for example, the plus basis means that we can initialize our circuits with a line of simply Hadamard gates, as the winning solution did, resulting in a circuit depth of 1. Now, this does make subsequent calculations quite difficult, which is why you don't typically see this kind of a initialization for most circuits. So while it's not typical, it is a correct and valid quantum initialization and should be looked at if you're trying to create the most efficient quantum circuit. You need to see what all of your possibilities are. Perfect. So here we had about 23 submissions, and actually quite a few contestants found this bit of trick of math, and we gave the prize to the first submission who solved the problem within the given error threshold. So congratulations, Yotam, for that. And here I'm going to go over and show how to do this in the Classiq platform. Perfect. So here we're going to go ahead and we have our variables defined. Here's our target L2 error that we specified for contestants, the sigma for the log normal, the number of qubits we have. Here we're calling a function that I'll show you in just a second, where we call in what are the probabilities we want to load into our state preparation. But performing state preparation in Classiq is as simple as calling the function state preparation, saying what are my probabilities? Well, the probabilities I want are these log normal probabilities I'm going to load in. I have n qubits, which is 10 for us. And we are telling the Classiq platform that we want to have an upper bound for our error. That's this L2 error. So don't generate a circuit that approximates it worse than this L2 error. Again, we call the model designer. We tell the model designer, prepare the state preparation with the parameters we just defined, and synthesize it for us. Now, to get this log normal probability, we have two ways to go ahead and do this, right? We have the standard discretization and then the kind of tricky discretization method. To do this, we used classic Python programming, where we define what the L2 error calculation is. And then we load that into our probability distribution calculation, which we use that L2 error to intelligently create our discretization so we don't go over that L2 error maximum. So we have a flag for if we want the standard spacing, and we have a flag, if the flag is false for us, we go ahead and use our log normal spacing. And all this function does is it outputs what our probability mass function is. Our discretization, since we made sure that one of the criteria for the problem was you had to submit what your discretization was, we have our margin and then our error for this problem. So I'm going to go ahead and load that function in, import Classiq. I'm going to solve this in the with the flag true, which means the standard discretization, so evenly spaced across all bins. And let's see what the Classiq platform comes out for us. So you can go ahead and see, as we've been showing you, this interactive circuit, or simply output a quick image to see what the circuit looks like. And here is the standard circuit. I believe this is a 246 gate depth circuit in the standard way that you would be going ahead doing that with standard discretization. But if we went ahead and called this flag false, we're loading in the same probabilities for all of our qubits, and the Classiq platform says, well, the best, the most efficient way to load in the same probability for all your qubits happens to be a line of Hadamard gates. So here you go, we're all set and done, and quickly and nicely, efficiently calculated.
Thank you, Eric, for that. And I do want to mention that both for this problem as well as all the other problems, the Classiq website on the competition section has articles for each of the problems showing 3, 4, sometimes 5 best solutions, Jupyter notebooks, some wonderfully detailed explanations about the approach for these. So for those that want to look at alternative approaches, I encourage you to certainly go and visit the Classiq website for that as well. So with that, let's move on to the multi-control X problem. And Hannah, the stage is yours.
Thank you, Yuval. So as we saw in the cockerel problem, MCX gates are essential to many different functions. We saw it there in our logical and, also in various state preparation algorithms and arithmetic comparators. The problem we gave the competitors was to decompose an MCX gate with 14 control qubits into single qubit and C0 gates. They were allowed up to 20 qubits, so there are 14 controls, as well as 5 clean ancilla qubits that had to be uncomputed at the end. And of course, the decomposition must be equivalent to the 14 control MCX. And then the valid solution with the minimal depth wins.
Excellent. And the winner in this case was Soshun from Japan. So Soshun, would you mind sharing a few slides to present your solution?
Okay. Can you see my screen? Can you see my screen?
Yes, we can.
Okay. Let me start my presentation. I'm Soshun Naito. I'm a second-year master student in the graduate school of Information Science and Technology at the University of Tokyo. Today, I want to share my solution for constructing 40 multi-control Toffoli gates. First of all, I'll show you the circuit. This is my submitted solution and submitted circuit. And this circuit can be executed in 57 time steps. So it has 57 circuit steps. And you can see, actually it's a little bit complicated, but you can see this circuit was constructed with 11 Toffoli components. These blue, light blue components are actually Toffoli components. Then I'll show you the key idea. And my solution has 2 steps. The first first step is to create small MCS gates, such as these components with reduced steps. And therefore, for these components, I created some approximate total gates, so to reduce the total circuit depths. And after creating these components, the second step is to find the best way to construct 4D MCX gates automatically. Automatically is the most important word. And I use the depth first search DFS algorithm for searching the best way to build a 4D MCX gate. So after implementing the automatic search, so after finishing step 2, all we need to do is to add topology components. So we just add small components and then automatically search for the best pattern. And about the step 1, I'll speak about approximate gates. And these gates can be constructed with fewer elementary gates, such as CNOT gates or 1-qubit gates. And these gates preserve basis and amplitude, but not phase. So they may cause phase errors, but phase errors don't matter because they are canceled out during the computation process. These five components are actually the approximate topology gates. And as a step 2, to find the best way to construct a 4D MCX gates, actually there are many possibilities for constructing 4D MCX gates. So we need to search every possibilities and calculate the circuit depths for each patterns. And I use these equations for calculating the output depths. For each topology component, the output has a depth of the minimization of the maximum of the summation. So using this equation, we can automatically calculate the circuit depths. So we can write a program to search automatically. And and this is actually the script and the execution results, and this is shown in below. I checked all possible ways using DFS algorithm, and theoretically, this algorithm requires an exponential time complexity for the number of qubits and number of ancillary qubits. But in this 4D MCX problem, the algorithm practically runs in a short time. So this algorithm practically runs very fast, and less than 3,000 ways were found. So so this problem was very effective. That's all for description. Thank you.
Thank you very much. This was great. And let me just show the distribution of the solutions. So we had many solutions submitted for this problem, starting from at the far left, you see Sochun's problem, and we had all the way to a depth of 1,000. And Hannah, if you wouldn't mind, let's see how we can create this both for 14 or maybe a higher control number with the Classiq software.
Sure thing. So there we go. So this is a very simple example. We import a few statements, define our constraints. We're limited on qubit count. We have 20 qubits, and we want to optimize for depth. And then we simply call our MCX function with 14 control qubits, and we can synthesize. I also have an example of a 50 control MCX as well, also optimized for depth. This one that is being created right now has a depth of 95. And the solutions that were submitted varied from 57 to 363 gates. So an interactive circuit should pop up any second now. If you want to see the very, very large 50 control qubit MCX, it's right here. And here's our 20 qubit 14 control MCX. So we can see in this interactive view how this gets broken up into the various Tifalis. And back to you, Yuval.
Thank you. And here what you're seeing, that interactive view, is one of the Classiq features that allows you to really dive into the circuit and see the details. So see how we solve the problem, this or the circuit of your choice. And so I think it's usually very instructive. So with that, I'd love to turn it over to our co-founder and CTO, Dr. Yehuda Naveh, to talk a little bit about getting into quantum computing. Here we into the industry. In the competition, we had anything from high school students to postdocs. So, and I'm sure many of the listeners are interested. How do you get into the industry? What's important to know? What should I study in college, and so on? So, Yehuda, the floor is yours.
Okay, thanks very much, Yuval, and thank you especially for all the participants in this panel and everyone who participated in the competition. It was amazing to see the amount of energy that young and old people have in looking into this field and putting all their creativity into finding such astonishing solutions for these puzzles. So once again, thank you for this participation, but more than that, this leads to this subject. Obviously, anyone who sits here and has invested so much of their time, energy, and focus in trying to solve these puzzles, obviously already has the huge passion that we see across many crowds of people who really listen and hear about quantum computing and pass beyond the hype and the newspaper articles and trying to look into it and trying to find out what it really means and what it doesn't mean. And obviously this population, the people that you are representing, obviously does not typically only care about studying the subject, but also working in it and more importantly, influencing it. So you gave some small influence in your participation and sending of creative solutions, but many of, I guess, you guys and others that you are representing want to influence this computing revolution in a very profound way. And this you can do in quite a few ways. Typically, it means investing, your work life within this field, and doing so can be, once again, done in quite different ways. One is from the purely academic perspective of becoming a leading researcher in the field in some university where you will have influence on the long term and what can be done in quantum computing and what cannot be done from a theoretical perspective, or as a researcher from an experimental perspective. Some of the quantum computers being implemented today are maybe the most complex and most sophisticated and genuine physics experiments being done, whether it is with superconducting qubits where they push the limits of what we call condensed matter experimental physics, putting the qubits in such a coherent way, or in neutral atoms or ions, where it's really pushing the limits of atomic and molecular physics, separating each atom from one another and controlling them by laser, each atom individually. It's, if you think about it, of course, it's a computing machine, but much more than that. It's a very, very deep and complex and physics experiments. So this is one way to going into being, at the front of academic research. Another way to go is participating from the industrial view. So as many of you know, quantum computing has reached industrial level in the sense that many vendors are building quantum computers, other vendors are building quantum algorithms, but more than that, and once again, I assume you know this, is many on the demand side of quantum computing, we see in all major industries, in banking, finance, oil and gas, automotive, aerospace and defense, and essentially travel industry, and essentially all major industries, we see actual enterprise customers who are building quantum algorithms using the vendors' supplies, such as algorithms, simulators, and quantum hardware. So this is another way to look forward if you are industrially oriented, either on the supply side of building computers and software, or on the demand side of building the best algorithms which will use quantum computers for your industry. There is really plenty of opportunities looking, forward. If you are in your early studies, say high school, senior levels, or graduates, or junior college students, you have an horizon of like 7, 8, or 9 years until you fully graduate. And once you are there, there is plenty of opportunities. So in order to capture all those opportunities, my small advice would be the following, and I will share my screen here in a minute. If I can, yeah, okay, it's here. So if I need to sum up my advice, except of course, keep your passion and make sure to be up to date in anything you do, the practical advice beyond that would be, if you are still at the junior college level, you need to pick the right major. Quantum computing is a discipline, technical discipline, and it's very hard, and I would say even impossible and counterproductive to think that you can contribute to quantum computing just by passion and thought and ideas. You really need to learn and understand the technical issues behind it. And this you would probably do either in a physics department or an electrical engineering department or computer science department, or in some stage, even in a math department, if you are very much theoretically inclined, but it would not come by studying things which are not technically related to that. In addition to that, as we all know, in today's world, it's not enough to sit in lectures. You need to really have discipline to read the most modern parts and the most modern items that come to the world on a monthly basis, but also keep the basis. And to keep the basis, I would try to, if I was very practically oriented in my advice, to choose your textbook that you feel comfortable with. An obvious starting point would be just Nielsen and Schwang that you are all familiar with, but any other textbook, because it's important to keep the basis together with the modern ideas. And also, in order to be in touch, there are many open source programming environments. You are aware of all of them. Go ahead and use your hands. It's important to make a field, to put the theory in practice. And one more thing that is quite unique to our community is the openness of the community. So all those groups of people that I mentioned, the academic people, the people who work in building quantum computers or in writing algorithms, and the consumers, the people who use the algorithms to advance their business, they are very open for reasons that I probably can explain, but this is a fact. So sometimes make a road trip to such person that you would like to talk to, or open up a 15-minute Zoom discussion, and you will get some nice perspective from different people, and these perspectives will help you, define your way in the details. This is an ongoing journey of like 6 or 7 years until you reach this position. So use these 6 or 7 years wisely. Look ahead, look to your right, look to your left. And this is done by reading, by studying, and by discussing with people. And obviously, keep fun in what you are doing, maintain your passion. Don't let it go away. But also, it's okay if sometimes your passion does go away or goes to another field. That's fine. Just recognize it and then make your decision. So I'm not sure whether we have time for questions. Of course, I will be available also offline. But this is my humble advice to someone early in their study journey who would like to feel the passion about this field.
Thank you very much, Yehuda, for your perspective. The article that Yehuda shared on the screen is also available on the Classiq website, as well as many other useful articles, demonstration, Jupyter notebooks, videos, both talking about the industry in general, as well as explaining our solution. So just summarizing, first, I wanted to thank all the participants in the competition, and especially Ozlem, Diego, and Soshun that were kind enough to invest their time in explaining and sharing the solutions. We spoke about the Classiq Platform that allows you to automate the process of converting an idea into an optimized hardware-aware quantum circuit and do it very quickly. We'd love to show you more if you're interested offline. The recording will be available in a couple of days. And the other thing, we have many other solutions from the competition on the website. I also wanted to thank the Classiq team, Eric and Hannah, and Yehuda, of course, for participating in this webinar, and all the people that you don't see on the screen for coming up with the idea, for coming up with the problems, for judging, and so on and so on. It was not a small effort, but we had an incredible amount of fun, and I hope that we'll get to do it again in the near future.